All right, now that we've talked about phase diagrams, let's get into some more specifics just with liquids. All right, so by the end of this, you should be able to give some liquid-specific characteristics. So, again, we're always trying to compare these different phases to the other ones. So just to kind of give you a visual of what your molecules are going to look like. All right, solid, everything is going to be super close. It's going to be really like organized in its structure most likely, and there's going to be little motion. All right, so we've got close, little motion. All right, liquid is going to have a little more motion and a little more space. Whereas a gas is going to have lots of motion and lots of space. All right. So, thinking about that, looking at what these pictures are showing us, what do you think the kinetic energy of these molecules are going to be? All right. So, what would have the highest kinetic energy? What would have the lowest? What would liquid have? All right. So, when it comes to kinetic energy, as you transition from solid to liquid to gas, and we've talked about this, you're absorbing energy when you do this, so you're increasing your kinetic energy. All right, so Ke goes up as you go in this direction. All right, so if you increase your energy, if you add kinetic energy, you're going to force something to go from solid to liquid to gas. Whereas, likewise, if you remove the kinetic energy, you're going to cause the reverse of that to happen. Gases are going to condense into liquids, liquids are going to freeze into solids. All right? So, if you wanted to melt something, what would you want to do to its kinetic energy? All right? So, think about what melting is. Melting is going from solid to liquid. So what would you want to do to the kinetic energy of that substance to get that to happen? And we talked about this last time as well. Intermolecular forces have a big impact on how well that kinetic energy is going to be able to cause a change in state. All right, so intermolecular forces, those are the attractions between neighboring molecules. All right, so if the neighboring molecules are really attracted to each other, that's going to counteract that kinetic energy. All right, so which substance is going to be more likely to, say, be solid at room temperature? Something with strong intermolecular forces or something with weak intermolecular forces? All right, and when it comes to phase changes and things like that, it's this balance between those intermolecular forces and that kinetic energy. All right, when the kinetic energy is able to overcome the intermolecular forces, that's when you can get something past solid state, maybe into liquid. And then if you really overcome those intermolecular forces, then you can end up being a gas. Right? Whereas if something has super, super strong intermolecular forces, it's going to be most likely a solid. So another component to the state of something is the molecular mass of the substance. All right? And this should make kind of intuitive sense. Just think about it. What can move easier, an elephant or a mouse? All right? When molecules are big and heavy, they just move more slowly. All right? So heavier molecules have less kinetic energy. All right? So keeping that in mind, what as the molecular mass gets bigger, what's going to happen to the state of the substance? All right. So, if you're looking at this, which would most likely be liquid at room temperature? If you think about it, our liquids are the things that are in the middle. All right. So they're going to have a middle amount of kinetic energy, a middle amount of intermolecular forces. So odds are the middle molecular weight is going to be most likely our liquid. All right, which one's most likely going to be solid? all right, which then means our lightest one is the most likely one to be a gas, all right? There's also this molecular mass can impact boiling points. And again, this should kind of like make intuitive sense, right? The slower something moves, the more likely it's going to be towards that solid end, all right? So what kind of mass is going to have super, super high boiling points, meaning you have to put a lot of energy into it in order to get it to boil? All right, so high mass is going to go with a high boiling point. The next thing that has an impact on whether or not something is a solid, liquid, or gas at room temperature is the shape of the substance. All right, and this factors into your intermolecular forces. All right, substances that can interact with each other easily, get really close to each other, are going to have stronger intermolecular forces, whereas substances that can't really line up with each other well and are going to have issues getting close to each other are going to have low intermolecular forces. All right, so like this guy here, if I were to draw another one right next to him, I could draw this really, really, really close. Just, it's really easy to get one right up next to it. Whereas for, say, substance B, if I were to try to draw this, like I could maybe start close here, but then I'm going to have to get kicked out a little bit because we've got these branches that are coming down. So those aren't going to be able to, get as close to each other. And then when you come into this guy over here, this huge branching system here is going to prevent substance C from getting close to another substance C at all. All right, so we're talking these guys have strong IMFs. All right, and these have the lowest intermolecular forces. So how is that going to impact your phase? Which of these substances is going to be most likely solid? Substance A, because it has the strongest intermolecular forces. So, some unique characteristics to water, all right, or just liquids, sorry. Water is a possible liquid. But some unique substances just to liquids are things like viscosity. So viscosity is defined as the resistance to flow. All right, so can you think of any liquids that flow really, really slowly? Like, if you're trying to pour it out of a bottle, it just moves slowly. All right, so things like this might be like syrup, or honey, or caramel. All right, those sorts of like really sticky things. All right, and just, kind of thinking about it that way. They're sticky. They're attracted to each other. Would viscous liquids have relatively high or relatively low intermolecular forces? High. All right, so the higher the intermolecular forces of a liquid, the more viscous it will be. Another impact that intermolecular forces can cause is this idea of surface tension. This is a unique characteristic to certain types of intermolecular forces. Water and its hydrogen bonds are able to do this. And this really doesn't have much of an impact on the state that it's in, but it just kind of gives it a unique characteristic, is that liquids with surface tension appear to look solid on their very outer surface. All right? And that is due to intermolecular forces between the molecules. And that's why this bug here, even though it's on water, can stand on it. It can walk on the water because of the surface tension. Another interesting thing to think about in terms of liquids is its property of vapor pressure. So when you are at the surface of a liquid, all right, so say you've got a cup here, we've got some water, all right, at this surface there's going to be a few water molecules that are breaking out of liquid state and turning into a gas. All right? All liquids have this. So some of the molecules at the very surface are transitioning between gas and liquid. All right? And vapor pressure varies based on the type of liquid that you have. All right? So if a liquid has a lot of kinetic energy, all right, those molecules are going to have an easier time transitioning into that gas phase. If a liquid has a strong intermolecular force, then it's going to hold on to its molecules better, so the vapor pressure will be lower. All right? So keeping that in mind, how do you think things like, say, temperature affect vapor pressure? Right? If you increase temperature, you're going to increase your kinetic energy. All right? So vapor pressure is going to go up. Pressure is related to gases. You're going to have more gas. All right? Now, think about it this way. What would increasing the pressure of your system do? All right? And this kind of ties us back into that last topic we had. All right? When you think about it, pressure, if you increase the pressure of your substance, right, you're going to kind of force the molecules closer together. You're just, it kind of acts as something against kinetic energy. And you can even see that pressure, as you increase pressure, things are more likely to be in your solid state. Right? So high pressures tend to have things in solid state. Right? It can be liquid as well, but then you have to get into some pretty high temperatures at that point. All right, but for the most part, your pressure's high enough, you're going to keep things in liquid, in solid. So if you increase your vapor pressure, you're going to if you increase just the general pressure, you're going to decrease vapor pressure. Now, one last thing I want you to think about this that might help kind of personalize it is think about boiling. All right? If you increase pressure, you're making it so that you have to put more temperature in to get boiling to happen.